And just last week, we have met again in Berlin for the kickoff of the High-Tech Agenda Germany, where AI and robotics is one of the 6 pillar activities where Germany will invest billions of money in the upcoming 4 years. And today, I want to give you an insight into the AI-powered industrial robotics, which is a major topic here at Fraunhofer IPA. And IPA is one of the founding members of our Robotics Institute Germany. So to give you a short insight about IPA, we had last year some brothers here, and they have a business. So they are flying with drones to facilities, and they have visited us, and they have flew to IPA. And here we are in the Future Work Lab, which is in the neighbor building, where we are working on the future of work. So how robotics, like human-robot collaboration or exoskeletons, are transforming the future of our work. At IPA, we have around 2 spin-offs a year in our institute. This is one, Celios, and here we are now in our big robot lab, which is inside this building. So, for example, for the battery disassembly, we are doing robotics since more than 50 years. That's our cable robot. And from there, we are leaving this building, going in the other one. We are looking to AI in action, for example. We are investigating assembly processes, which are mainly manual still today, into Industry 4.0, for example, for some food delivery. And then also coding is an important topic, also for automation, where Dürr is the market champion in this area, which is located quite close here to Stuttgart. And then we are here in the clean room. So we have the cleanest clean room worldwide, and we are certifying robots, grippers, but also chairs or tables to use them in clean rooms. So, for example, for smartphone production, battery or chip production, where we need to make sure that this robot is sufficient clean and does not create any particles which will destroy, for example, batteries. So also battery assembly is a topic, and now we are on the other side of the street, where we are looking into classical machining processes like milling, drilling, deburring, with a focus on lightweight production. So here we have the big machines. We are also training AI models, for example, to estimate the remaining useful life of time of such tools. And around that, at IPA, we are also doing consultancies like business model development, or then also brainstorming with our customers. So as this video is 1 year old, an update. So we are part of the Fraunhofer Society. So we have more than 30,000 colleagues within Fraunhofer, and IPA is one of the 70 Fraunhofer institutes where the major topic is robotics. So we have more than 1,000 employees, more than 1,000 industrial projects a year. So we are doing transfer from research into industry, around 100 million euro budget annually, and a focus on automation and robotics. So we are here in the headquarters, IPA Stuttgart, and since this month we have a subsidiary in Heilbronn. So Heilbronn is around 50 kilometers from here in the north, where we have a subsidiary with funding from the Dieter Schwarz Stiftung. So Dieter Schwarz is known from Lidl. From there he got rich, and now he's building up an AI campus in Heilbronn. And we have there also a campus on robotics, where we are working on an AI-powered robotics, especially robotic hands and humanoid robots. We will also show examples later on. What's new? So we have an outstanding infrastructure. That's also part of the WIC. So we have robots for industrial robotics, but also for agriculture, for elderly care, for disassembly, and it's stationary industrial robots, mobile robots, humanoid robots. So that's our infrastructure with which we are performing our research. Yeah, thank you to Daniel for organizing this lecture today. And we are here from the research division, automation and robotics. So we have 7 groups, which in handling processes and dexterity. So that's about robotic hands. Then also robotic processes like welding, automation planning. I will make this a bit smaller. Then force control disassembly is the group of Daniel. The navigation of mobile robots, software engineering, system integration. So we are coordinating the WAS industrial consortium in Europe. We will also have a conference 2 weeks in Strasbourg on that, and also robot safety and robots. When we are looking into our transfer story, almost every group has a spin-off. So we have, for example, in the handling one, the premium robotics, which is a roll-on gripper. It's a special gripper which is dedicated for goods which you are buying in the supermarket. So and here we are doing pilot projects with Lidl, for example, in their warehouses, because this gripper is possible to grasp objects from the bottom. So you can also grasp open articles like milk trays, or here also this alcoholic drinks. Then we have Assemblio. They are doing assembly planning using CAD models. So this is also a spin-off from robotics, because we were on the task looking, okay, we will have assembly robots in the future. And we were asking, okay, when I want to assemble this good, I need a plan in which sequence I will assemble this this machinery. And this led us to the question, okay, how can we automate assembly planning? And the twist was that we have now a module for assembly planning, but we have no assembly robots so far. But we are now using this algorithm to create assembly manuals for manual assembly. So this tool is used in classical assembly lines. Then we have DragonBot, that's about easy robot programming, like from the iPhone or iPad. And the latest one is Celios Robotics. So they are doing cable assembly, like cable wire harnesses, which are used in automotive production in cars. We have 4EM, which is a mobile robot company, and Node Robotics, which is doing navigation of mobile robots. And here we had initially projects with BMW, and meanwhile they have more than 1,000 robots in operation using this navigation system. Actually, there are a couple of spin-offs behind in stealth mode, so in preparation. So also in robotic hand, there's a spin-off in preparation. Also in mobile robotics, another spin-off, and the third one is in preparation in the area of human-robot collaboration. So when you come back in 1 or 2 years, we will see much more spin-offs in this area. And yeah, the question is, of course, AI and robotics, what's in? Is it 2 worlds? How can we incorporate them? Just yesterday, we had a big conference here, KI Congress, where we have discussed this also with NVIDIA. We have the bottleneck of data, but it's quite clear that currently these 2 domains are merging together, so that we are able to see also robots as a physical embodiment of AI. When we are looking now into the industrial robotics, we know quite well these production lines, body-in-white production. This is in Sindelfingen, so quite close to here from the S-Class, almost 50 years old. And this is a picture, and we see the changes are not really big. So we have still industrial robot arms with body-in-white, and indeed, this mass production is still there. So that's the working force of that robotics. And the question is, of course, what is new? What is really changing? And I have here an example of the use of AI in such traditional robotic cases, which was recently published by DeepMind and Intrinsic. Maybe you have heard about this robo ballot. So this is basically the abstract problem which we have seen in the picture before. So the application is that we have one workpiece, a car, and now we have the problem that we have to synchronize the movement of the 4 robots, which simultaneously are putting welding spots under this car. And Google took this challenge and used reinforcement learning on this challenge, and they were able to get 50% more efficiency in such a traditional progress. So before, engineers decided in which sequence which robot is approaching which welding spot. Now it's transformed into a reinforcement learning problem, and this allows to save 25% time in welding a car, for example. It's really incredible. And they have also found out that when I scale this problem if I use 8 robots instead of 4, so I double the amount of robots, I'm able to reduce the time even by 60%. And that's really incredible because so many engineers have thought about this problem, how to make automotive production more efficient. And now with AI, they are suddenly 25%. Another example from IPA is in the area of logistics. We all know that we have lots of AI stuff in the area of bin picking and image processing. This is pick and pack. So this robot can pick arbitrary objects, which the robot has never seen before. And at the same time, is doing also the packing planning. So it looks into the target bin, searches for an optimal point to place it. And basically the robot plays Tetris, 3D Tetris. That's really a nice one. And at the same time, it's really fast. So this video is real time. So this robot makes up to 1,300 picks an hour, which is less than 3 seconds a pick. And here we have the packaging planning. So we have like a online shop where we can put together our order, and you can see here how the algorithms are putting together the packaging. Sorry, I will shortly Teams. Sorry. And this algorithm is basically working in real time. So you can see it here. It takes the object which comes next and looks into the bin where to place it. And it typically allows for around 50% more density in the bin, which in the end reduces also the volume which is shipped every day. So it's also quite sustainable in this area. And without AI, this would be impossible, because before we were every workpiece, every article has to be taught manually. Basically, we have to say, okay, that's the article. Here you can grasp the workpiece, and here we have now really quite flexible robots. And we are now looking into the robot market worldwide. So what's the current playground in robotics? Every second industrial robot is installed in China. So China is the largest market for industrial robotics. Worldwide, every 8 robot is a cobot, like Universal Robot, for example. So that's 12%. We see a big growth in service robotics, so in robots outside manufacturing, basically, and a high disruption potential in humanoid robotics. And we see that this robot market is currently around 50 to 80 billion US dollar. And by 2030, so in 5 years, it could rise up to 200 to 250 billion US dollar. And we also see that currently it's about 10 to 15% AI inside, and this will rise up to 25 to 40% in the future. The market is quite well covered and investigated by the International Federation of Robotics, where we also are collaborating with them. And every year we are publishing the World Robotics Report on industrial robotics and service robots, where you can see, okay, how many robots are sold in which region and for which application. And you see here in the industrial robotics field that this market is currently quite stable, with around 540,000 industrial robots worldwide. But we have a growth rate annually by 11% when we look into the past. On the application side, the most robots are deployed in the area of electrical electronics and in the automotive industry. So basically, robots are building cars and they are building computers, smartphones, for example, or stuff like that. They can metal machinery, plastic and chemical products, food. And we have then also a big portion of robots which are deployed in other industries. And for this 73,000 robots, the robot manufacturer does not know where this robot is used finally. So it's unknown, basically. This is the overview from China. So 54% of these robots are deployed in China and are in German, but interestingly, also more of half of these robots are meanwhile also built in China. So China is building the robots for their own industry. And before, it was something which China imported, for example, from Germany or Japan, for example. And you see here that 80% of the robots are deployed in the top 5 markets. There's then Japan, the second largest, United States, Korea, and then comes Germany as the top 5 robot market worldwide. Next question is, what are these robots doing? So what are the applications? And this is quite stable over the last years. Every second robot is doing handling tasks like bin picking, palletizing, machine tending. Then we have welding a lot, like in body and white production, in automotive industries, but also in machinery. 9% is doing assembly tasks, so not that much actually. Machining 1%, and dispensing is like coating 3%. So that's quite a niche, and half of this market is done by Dürr and Bietigheim-Bissingen, quite close to Stuttgart. And quite worthwhile, 6% of the robots are operated in clean rooms. So they are in chip production, photovoltaic production, or in chip industry, for example. There's a second report on service robots, which covers transportation and logistics, like autonomous mobile robots, which is more than 100,000 robots. Hospitality, 42,000 robots. Cleaning robots, the professional one, which are cleaning, for example, train stations or supermarkets, for example. Agriculture, these are mostly milking robots. And then we have security and also other robots in this area. And this market is also quite strongly related to application domains. And for example, there's then the third application domain is the medical robotics, which is used in hospitals, for example, for surgery. And it's really quite interesting if we look into such systems like the Da Vinci knows everyone, which is for from Intuitive Surgical, which is also on the text listed. And when we are looking into the market capitalization of this company, which is developing the Da Vinci, it's $185 billion. This alone Intuitive Surgical And I have here the market capitalization of the largest automotive manufacturers worldwide is Toyota, sorry, it's Tesla, 750, Toyota, 210, BYD, 131. So the 350 vertical is somewhere here. So it's from the worth on the stock exchange, it's worth so much like top 3 automotive car factories that are manufacturing. So that's quite impressive how robotics is strong in niches. When we are looking into the application, so that's a video from Node Robotics at BMW. So here we were deploying these smart transport robots. So these are using the Fraunhofer software for navigating to the final assembly. So that's a screencast from Regensburg. So that's a warehouse, and then it's moving to the final line from the BMW assembly. And in green, that are the laser scanner data. And we can see how it's navigating through this dynamic environment. So there are persons walking, cargo trains, forklifts, and so on. And it was quite interesting. In the beginning, this robot had a crash. So BMW called us that, hey, your robot had a crash. It was crashing with a forklift. And of course, as it was a new robot, we thought it was an error of the robot. And we then investigated into our log files. And we were able to prove that the robot was not moving in the moment of the crash. This means that the forklift driver was chasing the robot, basically, because the people were afraid that the robot is stealing the job, basically. And that's something which we are learning a lot. So when we are going with new robots in the shop floor, the people are a bit afraid that this robot is a threat for their job. And therefore, it's not only a technological question, but also a personal question if the people accept this robot as a colleague, basically. There's been another example in agricultural manufacturing. So they were working in ghost shifts, basically. So they have implemented a welding robot, which was working autonomously. And that was really nice because the blue collar worker, they were implementing the robot. So they were programming it. They really said, oh, that's our robot. We like it. And in addition, the worker received a salary for every hour the robot was welding autonomously in the night. So this means they were highly motivated to select then orders for the robot, which they put in the afternoon. And then the robot was operating overnight autonomously. And in the morning, when the robot was welding the stuff, they have received additional salary. And you can imagine that they were quite happy with the robot. And that was an example how to implement robot in the shop floor and how to also have good relation to the robot, actually. That brings us also to the welding robot. So we have seen that the cobots is quite an important market worldwide, 12% for industrial robots. So these robots are at first fenceless, basically. You can teach them quite easy because they have a graphical user interface, and you have also hand guiding functionalities. And what we have, but they have also a gap. So if a cobot is taught once, it always makes the same movement. So it has basically no intelligence. And when it comes to welding, we have the problem that we have different geometries. So that's the weld team. And we have also tolerances. So the part is not stitched quite precisely. So we can have also different parts. This means, again, we have quite high programming efforts to account for these tolerances. And what we have developed here is a sensor add-on, which allows the robot to detect the beginning of the weld seam and to also compensate for all the tolerances, like heat tolerances during the welding. And that's really a game changer because it reduces the programming efforts dramatically. And like here, you can then stick together also modules, for example, for this rectangular tube there, where it's checking then for the weld seam. And this allows for a really fast programming. And one of the success factors here was that the team has a high level of knowledge in welding. So the team leader has been working for a welding company before. The other has an education as a welder, and the third one was working at Mercedes in the plant. He was there's this safe S-class with the high with steel plates inside, and he was welding the steel plates into the S-class for 1 year. So the team has a big knowledge how to weld, and this allowed us to develop a solution which is easy and which also found the way in the market. So this software add-on is now commercially available at Law and also at home because it really allows for high-speed programming in this area. So it allows us to change or adopt for positioning errors, assembly errors like here. Also, if the shape is different, and also if the workpiece is changing its geometry during the welding because of the heat which we are introducing through the welding. So so that's basically done for us. Also, there's always here a check mark. So for research, no research question left. But we are at IPA, so we always find new challenges. And the next challenge is the multi-layer welding. So in the beginning, we were only able to weld one weld seam, but now we have extended it, and that's a current research activity for multi-layer welding, which is used, for example, for construction machines, for example, at repair. So there you have constructions where you have to implement 50 weld seams into an assembly. So it's really incredible, and that's a manual task today. The same applies also for security applications in the defense sector, and that's then also a current activity where we are looking in. The other activity, which is not shown today, is that also chipless welding. So the idea that 2 robots are manipulating the workpieces and the third robot is welding. So that allows them also for autonomous welding, for example, in ghost shifts. So, so this allows us for the production of assemblies. But then a new emerging topic is also the disassembly. So in the circular economy, and what we will have here, also a regulation in Europe that, we are obliged to use also recyclate. So this means when in 2031 a new battery is manufactured, the manufacturer is obliged. He has to use recycled material, basically. So 16% cobalt, 85% of lead, and also lithium, 6% of recycled lithium. At the same time, we have much more electric cars on the road, and this gives again an opportunity for automation because when the electric cars are at the end of the lifetime, we have to disassemble them, go into a recycle process. And so there's a big volume. It's also dangerous to open such a big battery, and therefore it's again also a task suitable for robotics and automation. So we have a big toolbox of different processes like fastening, assembling, plugging, pushing, clipping, handling, snapping, inserting. So we have a big set of skills which is now used for the robot-based disassembly, for example, of such electric car batteries. That's really interesting because it's quite challenging. So this battery is 5 to 10 years old. So there has been maybe was repaired, for example. There's also dust on it. We not necessarily have the CAD models of this battery. And this means we again need quite a flexible robot with AI capabilities that we are able to disassemble, something like this. And so this question of disassembly again motivated several research questions. For example, okay, how can we detect how is this assembly constructed? What are the fixtures used? Where is the screw? Can we unscrew this battery, or do we need to make it mechanically to open the battery? With which kind of tooling can we open it? How has the gripper to be designed? And how in the end can we go for economical and robust feasible automation solution? And this is for electric car batteries, but here on the right, we've also investigated this for all other kind of goods, like also this assembly of robots actually. So here down in the lab, we've also lots of old robot vacuum cleaners, and here we also implemented a robot which is able to automatically detect and remove the battery in a vacuum robot. And we see that this is a really emerging field, and also lots of customers approaching us, and they want to implement such tools because they see now they want to build up such remanufacturing factories, basically. That's really interesting field. And you can imagine that this is also high-tech robotics. So we are using vision language action models for the control of the robots, skill-based programming for the force control parts. So we can really use all the research results in robotics to solve this challenge. So that's the one hand side on the robot skills. When we are then looking into the more system side, we have such an iceberg. Still today, we have this nice industrial robots, which is only the top of the iceberg, basically. So we have the industrial robot arm, which comes from KUKA, ABB, S-Tool, Yaskawa. But there's still a big way to go to make a complete robot solution out of it. So you see it here that the robot makes only 1/3 to 1/5 of a complete robot solution. So we have to invest into safety systems, into grippers, programming installations, project management. This means the robot is basically the smallest part of the investment. And therefore, we are also looking into the so-called automation of automation. So we are looking how can we lower the integration efforts of the robot. And here, one focus topic is the safety of robots. So for every robot we deploy, so for every 542,000 robots worldwide, we have to make sure that this robot does not hurt any person. This means we have a robot process, like here, pick-and-place application, where 2 robots are working quite well. But now we have to check, okay, where is a human? Where does a human could get hurt? And that's quite a big engineering effort. And we made a survey, especially for collaborative application, where small, medium-sized enterprise said 50% of the engineering costs comes from safety considerations, and in large companies even 20%. So a big portion of this iceberg is safety. And so they are asking for a tool that guides safety stuff. And almost everyone also says, also using humanoid robots, the safety question will even get larger than today. And this is also then led to research question, which is under the umbrella of CARA, Computer-Aided Risk Assessment, which is a tool which is automatically identifying hazards. So it's checking the workspaces of the robots, checking the workspaces where a human can enter. Then it makes suggestions for the risk. So it says, okay, which hazard is it? Is it a transient, entrapment? What is the source? So what is the collision which might happen? And then it helps the engineer in decision making if this risk is acceptable or not. It makes then also a position of safety measures like fences, laser scanners, reducing the speed, using a robot with power and force limitation. And in the end, it guides through deployment and helps to get from an unsafe robot to a safe robot much faster. And in the validation project, we have found out that we can reduce the engineering effort by 54% using CARA. How does it look like? You can see it here. So that's a typical scenario. We have the robot doing the pick and place stuff of this heavy work pieces, and the human is there to adding something which is not that heavy. And now we are in CARA, so we are checking, okay, where are the hazards? We are visualizing the results. So in blue, that is everywhere where the human can walk. Then we have the robot reachability, where the area where the robot comes in. And then step by step, we are investigating the risk of this application. We are also then have a human approximation model, which says, okay, when a human is standing here, it can still reach that position, which allows us then also for such entrapment investigations. So then we can also look into the pressure. So we will see this later on, that we are allowed to have collisions with the human if it's limited, according to the ISO TS 15066. And then we are going into the risk assessment. So for each risk, so here it's more than 50 individual risks. We have to make decisions if it's acceptable or not. And so without CARA, you would use Excel basically and do your own tool. And by this digital tool chain, we are quite faster. So now, so meanwhile, we have made some decisions about the safety measures. So implement the fence, for example. Also safeguard here. And then that's again a bit tricky, because now we have a fence, but this fence again introduces new hazards. Because now there could be happening an entrapment between the fence and the robot. So we have to reconsider the risks again. Now we are done. And tada, that's the final result to make this robot application safe and also quite fast. So that's this tool is currently in beta testing since 1 week, and it's also one of our potential spin-offs of IPA, which is under preparation. Now, looking into the last section of humanoid robots as an outlook. So embodied AI in action. So we have here the conversion of AI and humanoid robots. We all know this famous videos of Boston Dynamics, or also figure about this pilot installations, which is quite impressive in, for example, in handling, also in machine tending in the Spartanburg plant at BMW. And we also see lots of funding going inside this area. So just last year, I was reviewing a strategy document for the European Union. And so there it was stated quite proud that the largest European robot funding program, Spark, it was the largest robot program in the world with funding of 700 million euro for 6 years. And so they were proud. And almost at the same time, Figure AI received 623 million euro in one funding round. So one robot startup almost received the same amount of money like the complete European robotics research in 6 years. So that's just to give a scale how much money is spent into the humanoid robots. And just this spring, there was also the half marathon in Beijing, where 23 robots started. Around 5 robots made it into the target. So they made this almost 21 kilometers. And it was really an impressive testing of the mechatronics. Of course, they were allowed to change batteries. They were even allowed to change a complete robot. But we see that China is pushing a lot in the area of humanoid robots. I've been there 4 months ago on a delegation trip, and it was really impressive how the companies emerged. They started 2 years ago and were able to join the half marathon after 2 years of development. There's also a robot museum in Beijing, Beijing Humanoid Center, where we were able to see some robots, for example, then also for coffee preparation and also for pick and place. But it was really slow, and also the robot was not walking autonomously. It was also with this guidance here to avoid falling, for example. And we have also here at IPA Unity G1. I guess lots of RIG partner have a G1. Also, when I'm looking back to our meeting in Bonn, I guess I see 2 or 3 G1s. So that was the unboxing. So removing the foil, putting the IPA sticker on it. That was this summer, this video. And it allows us to gather some real world experience with the humanoid. And just today we are doing also a benchmarking of this robot. So we have installed a parkour downstairs in the lab. So with obstacles and slopes to investigate how stable the robot is moving actually. But nonetheless, so we were asking us the question, is a humanoid robot a game changer or is it a hype? So what to expect? So we asked more than 100 companies, so both system integrators, but also end users. So end users are people who are running a production side or logistics side. And we were digging into different kind of questions. For example, application scenarios. So what would be the first application the companies would like to realize with humanoid? And it's quite clear that the most have in mind the material transportation tasks, so 84%, machine tending, gripping complex objects, so everything with pick and place, especially when the robot can load one machine. When this machine is done, it can go to the next machine, load there. And if a third machine needs parts, the robot can also move to this machine. So we have this kind of, that the robot can jump from machine A to B to C. We have also implemented such a simple use case of our G1. And so here it's now picking this bin. It's using its hands and then taking this box to another position. One must say that this operation was completely teleoperated, so there's no autonomous operation on board. There's also no inverse kinematics from off the shelf. So this is really teleoperated, like almost, I would say 90% of the G1 demos we see are teleoperated. So that's important to notice. We then also asked our industries, so which end effectors do you need? They said 42% modular grippers, so they want to change gripper. So, for example, two-finger gripper, change it to a suction cup or something different. And the other one said we want robotic hands. So we not only want a humanoid robot, it should also have hands like a human. We also looked into the locomotion, and here it was the case that they are saying only 40% want that the robot has also legs. 56% say, I don't bother about the legs. It's okay if this robot has wheels. I'm only interested in the upper body, for example, in the dexterity skills. And so this is really an important finding, and we also can see this in the market. So more and more humanoid robot manufacturers are putting their humanoid body on wheels, basically, because it's cheaper, it's safer, and less complex, basically. And from the skills, they want to have indoor navigation so that the robot can move from A to B autonomously. It can check the environment, it can localize and sort objects, walking on flat grounds, and also carrying loads. So that are the major skills the German industry in production logistics wants to see. When I've been in China, I have seen also lots of work in the area of robotic hands. That's Robotera, for example, and different robot hands. And so still today, it's not clear how the robotic hand will be designed. So how many degrees of freedom will it have? Will it have 5 fingers? Are 4 sufficient? It's quite clear that we need a thumb, and how to make it robust and how to control it. So here we had then also this with Apple Pro, we were able to control this hand. We also visited Linkerbot, and so Linkerbot is one of the most advanced robot hands, and so they have still some robustness challenges. So they said they have a mean time between failure of 100 hours. So every 100 hours there's a failure of the robot hand. So this is really a big challenge. We know the shadow hand, for example, from UK, from Rich Walker. He wants to stay in research with his hand. It's not useful for industrial application. That's really challenging. And this is now one project which we are doing in Heilbronn, where we are investigating the control of robotic hands for assembly and picking processes. And one of the major challenges which we want to solve is the in-hand movement. So we want to allow the robot to pick out an object in this orientation, then to move it in the hand, to place it in another orientation. We have seen something similar already at DLR, for example, at EU Robin, so in Oberpfaffenhofen. And I guess now it's really the time to make such applications industrial proof, because we see that we need more flexible gripping solutions in assembly, for example, in bin picking. So we have now over decades used 2-finger gripper. Now it's time for robotic hands. We back to the study. We also asked about challenges So the most people said, okay, human-robot collaboration with humanoids is challenging regarding to have it legal, especially in Germany. We have safety people walking around. We also need a revision of the machinery directive. Since early this year, there's now also an ISO working group which takes care of safety standards for humanoid robots. We have just met for the third time last week in Barcelona. We want to prevent hazards for people. So the humanoid is quite sweet, but it's also dangerous. We will see this later on. There are also some investigation that a humanoid robot could be a spy, basically. So there's one paper about Unitree which say this robot is collecting lots of data, and it's quite easy to hack this robot, to receive access to the robot, and to steal the data which the robot has gathered. So there's really a big deal, several issues which have to be tackled. And we have started with a norm or a definition. What is a humanoid robot? So we say a humanoid robot must have a human-like shape with an upper body and 2 arms. Typically have also 2 legs or something suitable for locomotion. So a humanoid is nothing which is fixedly installed on the bottom. And it might have also grippers, and it might also have a head. We have sensors for detecting the environment, and it also has autonomy functions, but it might also be just operated remotely. So that's the humanoid robot. But then we have the humanoid robot system. And this means we make now out of this robot robot application. And for this purpose, we have also safety measures, like a safety sensor. We have tools so that the robot has a tool and effector to interact with the environment, and also components like workpieces, for example. So that's this well-known example. There is no safe robot. There are only safe robot applications, and it's always the question: is this robot manipulating, for example, a rigid object? Then it's potentially safe. But if it's operating a knife, which is sharp, then you will never have a safe robot application. And what we did, we investigated the forces which our G1 is performing or exerting on his environment using this safety measuring device, which we know quite well from the robots. So we were investigating real-world events, like robot is moving on the table, hurting the shoulder, like this. And this allowed us, the robot, to compare this now with the safety standards. So we have a pain atlas. So has been research done which pain is acceptable in which area of the body. And we see that it's about yellow to red. So 190 Newton on the hand is really quite acceptable. 19 kilo to the side is also okay. So that's here we have observed quite acceptable, but we have also seen that we can increase the speed of the robot. We can double the speed of the robot, and then the forces go up to 500 Newton, so 50 kilogram. So it pushes with 50 kilogram on the table, for example. It then becomes unacceptable. So in the end, we see that this robot is dangerous, basically, if it does not behave than expected. And it's also the same when the robot is walking. So in the forward collision, with here, for example, with the shoulders, 380 Newton, with the chest, more than 500 Newton. So this robot, which is quite a small one, so the G1 has a weight of 35 kilogram, it's 1/3, something like this. It's a small robot, but it already can hurt people quite a lot. So that's important to know. And that's also one of the, again, obstacles for humanoid robots, non-regulated safety. So there is no safety on board yet. The manufacturers are working on that. We have maybe also too high expectations. So when we are looking into the media, we think with humanoids we can solve everything. And then also the question, okay, how do use cases look like, which are economically feasible, and how does the programming of these humanoids working? And here's one use case we have investigated. It's a material transport application. So we have production lines reporting working stations, and the robot is supposed to pick a box and transfer it to Kanban shelves. In average, it's around 35 meters to walk. We have then a 2-shift production, and so that are the assumptions. We have battery runtime of 2 hours of the robot, and with this application, the robot has a productivity of 50%. So it's not completely used. So it could basically do the double of the work. And we have then made a economically study using that the robot, including integration, is around 100,000 euro. We have again 15,000 euro engineering costs. We have also energy costs, maintenance costs. So that's what's the robot. We have then also labor costs on the other hand side, and then we can compare it basically, and you can see it here. That's the typical thing. When we have a manual process, we have low fixed costs. We have only variable costs. So every month we have to pay a salary, and this is because that this slope is quite high but starts low, and the robot is a one-time investment, but then low cost after we have purchased it. And in this scenario with these assumptions, we have a return on investment after more than 4 years actually. That's quite a long period. As we were also surprised how long it is. But we really have to say that the robot is only used 50% of his time during the 2 shifts. This means it could do a 3rd shift, and it also could take over a 2nd task during the day. And using a 2nd task, we would be able to reduce this time to somewhere on 2 years. Then it becomes, I guess, quite interesting. And of course, the robot will become also much cheaper in the future. So when the production numbers are rising, so maybe they're not 100K, but only 50K, then of course the break even is also much faster reached here, for example, probably after 2 years. So, but it's just an example to give something of a feeling how an economic use case could look like. And we really see also still a way to go, that these robots are mature. As IPA, we are investigating and visiting lots of shop floors, production sites worldwide. I'm also asking lots of people, did you have seen a humanoid robot in production? And every time, no. Also almost no one has seen a humanoid in production. There are some flagship pilot projects at Mercedes, BMW, for example, which you know quite well from videos. but behind that, humanoids are in the labs, and you see here for the maturity of the technology, 6% see it mature in 3 years. 74% say, okay, it's 3 to 10 years. And then in 10 years of earliest, 14% or 6% basically say it will never be there. And so we know quite well when discussing also with the manufacturer, they see a mass production, mass adoption somewhere in 2 to 3 years, basically, where we will see humanoid robots in production. Today, the most applications are really in research and in pilot projects. And there's another important thing. Jump back to this one. So this robot, it has 29 degrees of freedom in its body and 14 degrees of freedom in its hands. So more than 40 drives, more than 40 actuators which we have to control. And this raises, of course, also a question, how do we program these robots? So we cannot program this robot with a teach condor in the future. So we need also AI or new and intelligent ways to program them. And so here, the most promising approach is the combination of stimulation with imitation learning, so that we are using systems like here this Aloya arm, which allows us to guide the robots, that we can show the robot how to, for example, open this door or close it here. And so we are doing data generation. And we know that, for example, at DeepMind in the US or Boston Dynamics, lots of data generation is done using such systems. Also in China, there are data factories, basically, where people the complete day are guiding robots and they are demonstrating, for example, how to move an object or how to fold a t-shirt. And if we combine this with language instructions, then also with vision language action models, we are certainly able to also control such high degree of freedom robot systems. And so we really believe that this is the future, because it allows us to automate tasks which have never been automated before, and also in a quite flexible way. So in the end, we have robot skills, like in PyTask, for example, which is a software modules which are really well developed for force control, for example. And using such approaches, we are able to select the right skill for the right task, and are then able to grasp such a ball, but also making machine tending, or also something like this, that we are able to operate a machine by pressing the right button, which is in the end also a force control. And we are doing this here currently on a universal robot arm. We've just this day received a new teleoperation device, which also gives us force feedback. So we can also feel what the robot is feeling, which allows us then also to train quite a contact-rich assembly processes, for example. And I guess that's quite an interesting time ahead to look into such systems. Now I will check if I can. Yeah, I will move for the next slide, but this one needs sound. Maybe we can do like this. So I hope it comes also to the micro, but I think so. Some years ago, we were investigating what our robots are doing at night in our lab, and it was quite a funny project. Yeah. Yes, so as we can see, our robots have fun, and I hope you also enjoyed this lecture. Now I'm open for your questions. Thank you.
Okay, so for questions, you can raise your hand, or if you're in one of the classrooms, I guess you can also start speaking. Or you write on the chat, and I will relay the question.
Yes, yeah. One question.
Thanks a lot. That's great. So my question is, I mean, since this field is moving so fast, and especially with the development in the AI, it will be moving even faster. The current robots now produced and bought by the companies, they will be probably outdated in a couple of years, right? And if it continues like this is not going to work clearly. Maybe we should think about maybe some kind of modular design for these things, that's replaceable arm. I don't know. I mean, you tell me, what are the thoughts on that part?
Yes. Yeah, it's a good question about, okay, what's about how can we upgrade these robots? And so we have a operational stock of industrial robots, about 1.5 million industrial robots worldwide. And we also experience this, that if we want to incorporate new algorithms on an older robot, they always say, okay, oh, you have the CB3, okay, this one is perfect fine, but you have a CB2, no, you cannot upgrade this. And we are, I feel the feeling in that area we are still in a stone time. Of course, we have with ROS, we have quite a good base that we can upgrade robots, and also with ROS Industrial, we see them also in the production. At the same time, we have the platform like Intrinsic with flow state, that we are able to make software more reliable, also more durable, and to make upgrades. But this is indeed a big challenge, and also regarding there's still the saying, okay, never touch a running system. And so I guess something which we have in the AI field, like DevOps, that we have also tools which allows us to check, okay, will this update of the software still work on this older process? And is this process, this robot still stable with the latest software? I guess that's also an important research question, which we have to solve to make something like this happen. But it's really it's challenging. And yeah, we also always get approached by customers which say, oh, I have bought old industrial robots from Mercedes. So they have worked for 10 years. And now I want to automate with this old robot. Yes. And then we always say, okay, you have to build on the one hand side, you need a new gripper, new safety system, and so on. It's not only the robot arm, it's much more. Yes.
We also have some questions on the chat that I can read in a second, but before we do that, anyone else, maybe from KIT or so on, do you have any questions?
Yes, I'm. Okay. Okay. I have. Okay, yes, I will. Yeah, I will. Have you experimented with VLAs like CRUD or Pi0? If so, what were your results? What might be typically problems, implement them, and how to solve them? We were also looking into these tools, especially when it comes to the disassembly stuff for screw detection, for example, but also for the handling one. We were currently more looking into NVIDIA Omniverse, and we are currently in the process to make also data generation to augment these tools. And so the results were quite promising, but it honestly felt, as it felt a bit like as when we see the pick and pack, it makes 1,300 picks an hour quite fast. And if you are using like these models like CRUD or Pi0, it was quite slow actually. But it felt a bit maybe like a transformation when we are using the cameras. So we have the analog cameras, which makes quite pretty pictures, and the first digital cameras, which made worse picture. But we have seen there's a big potential behind it, and somewhere we are in between. There's a big potential in these foundational models in VLAs, but we are not there yet. So they are not from the performance comparable with state-of-the-art methods which we are using in Build2Build currently. And there's a question from Gabriele. Hello, thanks for the lecture. I have a question about the picking and packing task. How well do the robots deal with several constraints and conditions? For example, do not mix edible products and cleaning products while packaging, and do not put tomatoes at the bottom of the box because they are soft. Yeah, excellent question. And indeed, we are able to deal with stuff like that. So it's a question of the detection. And from the early beginning, we are using SAM in the detection. So we are also able to detect also the text which is written on the workpiece. So we can also look, for example, for orange juice in the bin. And we have also integrated this with a LLM. So we can really ask the LLM to only grasp the red workpieces, for example, and to also bring reasoning capabilities in this application, which allows then exactly for something like this, that we can integrate constraints. And that's also what our customers are asking us. So they also want to avoid, for example, that with a threat that we are putting a fragile object in the bottom of the box and put something heavy on top of it, so that nothing gets broken. And that's reality, and that's also what is not shown in the video, but is available downstairs. Then there's another question. Thanks for the great insights. Where do you see the biggest unsolved need for automation in industry? Which hurdles do we need to overcome to solve it? Also a good question. Probably one could talk about this another lecture about the biggest challenges. I see a biggest challenge currently in what we have in research basically. So we have lots of VLAs, lots of AI-powered robots. Every robot has a sensor. And when we are then looking into industrial practice, they are looking for much simpler solutions. When their robot has a camera, it's already a lot of stuff going on. And when we are looking into maybe more reality, we also see calibration issues, for example. And I also know it when we are going on trade fairs, then every night the robot camera, as a hand-eye calibration, is recalibrated because it get lost. Or like here, when the sun is shining into the room, it's also disturbing the robot eyes. And also therefore, there's a big challenge in getting this stuff robust. And so for us, also in the Robotics Institute Germany, I guess the biggest challenge is to introduce this domain knowledge to completely understand the challenges which industry has and to translate it into robotic solutions. When I'm referring to this welding example, we were researching the welding stuff over a decade before with offline programming, 3D sensors, and there were several PhDs working on the welding, but it was much too complex. We run into accuracy stuff, for example. Also, we had a need of a offline programming software, which alone was 20K only for the software without a robot. And so there was no way to bring something like that into industry. So that's also means as robustness on the one hand side, but then also the big leap will be this interoperability, that we have really an Android of robotics, that we can put together the components and they fit immediately without further writing glue codes, testing the complete system, writing PLCs, and so on. There's too much handcrafted stuff outside the automation.
Yeah. One question for me from the KIT. First, thank you for your lecture. And then you briefly talked about the ethics of involving robots in work. Have you made any research about the amount of jobs that could be lost or possibly even created in the involvement of robotics?
We don't do the research our own, but when we are looking into the statistics which are available, we see that the countries with the biggest degree of automation, which is the robot density, which you probably know, so how much robots are in operation per 10,000 workers, that the countries with the highest robot density, they have also a big employment rate. So they have no problems with unemployment. So in the end, we see that the use of robots, from industrial robots, they are contributing to the growth of the economy, and that the robots also enable that production stays in the countries, which allows them also for employment around the robot, basically, for example, in service sector, in administration, and so on. Therefore, we clearly see when we're looking into the past that automation is important. It creates jobs, actually. And when we're looking into the future, we also see that also worker councils are asking for more robots, basically, because they know about the retirement of the workforce in the future. And I guess the contribution to the economic growth, also Bruttoinlandsprodukt, I guess was 0.3% growth per year was industrial robotics in the past. It's not much, 0.3, it sounds not much, but we have this synthesis effect, so it's accumulating a lot.
Okay, thank you.
Then there's two questions from Peter Mauritz. Thank you for the great lecture. What would be a good starting point for indoor and outdoor AMR developers to implement AI into their robots? It's basic. I mean, we have to definitely understand the use case. Okay, where can AI help us? And so, for example, when we are looking into AMRs, there's lots of stuff going on that currently they are only using 2D laser scanners, and you could use, for example, then a YOLO model to detect people or to detect, okay, what's going on in the environment, and quite easily create new information which can be used in the navigation, for example. For the idea that the AMR is able to detect people before the safety scanner is detecting them to create collision avoidance paths. for example. Then the second question, how do you see the need for AMRs with manipulation, mounted cobots, and the advantage of AI integration with the system to get better products, just vision and more perception? It's really a good question. So this mobile manipulators, which is an AMR with a cobot on top, is currently not a perfect product. Basically, it's a bit like in the car industries. When I'm looking for a parallel, when we are using a combustion engine car, we are removing the combustion engine and put a battery and electric drive inside. So it does not feel like a good product. And this is because we have two separate controllers in the robot. One controls the AMR, the other controls the robot arm. And the first thing we need is that we have a single point of control, so that we can have one controller which controls the arm and the AMR. I've just recently saw something like this, like for example, you can then control the arm and the base, so they can make also null space movements, which is important. And then we also need such kind of imitation learning approaches, because we have also too much degrees of freedom, which is too hard to control or program them in a classical way. Still, a problem or also challenge is safety, and together with the speed, because when we are putting the cobot on a mobile robot with typically fenceless application, and which lacks also of cycle time. So it's then also a combination of perception, compensate for tolerances, but also future developments towards safety systems. Then, Peter, thank you for the presentation. It seems that China and the US are leading this field, while the EU is less active. Do you share the view? And if so, what do you think are the main reasons for it? What be done in Europe to strengthen our position? Yes, also, we had also this just yesterday a presentation about status of China, and it's really impressive. Also, maybe some of you have been on the IWAS in Guangzhou 3 weeks ago, and it's reported that 100 to 150 companies are developing humanoid robots. And in Europe, we have the challenge that we have too much regulation with AI Act, Cyber Resilience Act, which is really a break in the development. And also companies like Boston Dynamics, they avoid Europe basically, or the European Union, because it's too complex to deploy robots here. But they say UK, for example, is fine. This UK AI Act does not apply. And I guess what do we need? We need to build on our competence, especially in WIC. So we have the best research centers together in Germany. We have a similar project also on European level, EU Robin, and it's now the time to receive also funding to strengthen the forces and to also investigate more into the AI-powered robotics, and then also looking into the verticals like the production, agriculture, logistics, but also medical applications, to bring as a robot to life. And when it comes to embodied AI, there is still something to win. There, the game is not finished yet, and therefore it's really important that we have this week in Germany.